Hello everyone, this is Professor Chan for Math 1245 for the online section. Today we're going to be going over section 2.2. We're going to finish the rest of it. We're actually going to do increasing and decreasing functions along with piecewise. Okay, so when we're talking about increasing and decreasing functions, right, it's pretty straightforward. Increasing is when our graph is going up, and decreasing obviously is when it's going down. If it's not increasing or decreasing, it is constant. So that is one thing we're going to analyze, okay? So we are going to look at a graph. We're going to see if it's increasing and decreasing. We're going to write in interval notation. And then we're also going to identify what's called local max, mins, absolute max, and absolute mins, okay? So we actually have two different types of maximums and two different types of minimums, okay? So I'm going to kind of briefly describe the local max and local mins here. Okay, and as you can see here, and if you're looking at your textbook, if you're looking at the PowerPoint, the definitions for local max and mins can tend to be a little bit wordy and it can tend to be a bit complicated. Okay, so let me kind of give you the breakdown of how local max and local mins work, right? So what is a maximum, right? A maximum essentially means it is the highest point. Minimum means it's the lowest point. So when we're talking about a local max or a local min, we are essentially saying the following. So suppose that you have this large picture. Local essentially means, right, it is in a specific boundary, right? So if you think about, for example, America, right, America is national, and if you're looking at a local situation, right, you're looking at something like the city of Marion or the city of Columbus or the city of Cincinnati, right? Local, right, is defined in a specific boundary. So when we say local max, we are saying the maximum in a specific boundary, okay? Or when we say local min, we're saying a minimum in a specific boundary, okay? Now, the asterisk right here that I'm showing you, that if you look at this cursor right here, that's also important, is local max and local mins essentially has to be the smallest or the largest on both sides, okay? So, for example, I'm going to sketch this right here. Sorry about that. So local max and a local min. So local max means it has to be larger on both sides, like the following right here. Okay? And when I'm looking at, right, and for example, this is my maximum, like this. Okay, this blue dot is my maximum, and it's my local maximum because at that particular area, right, it's larger on both sides. Okay? So I could also have something like this as well. Okay, like kind of an upside down V shape, and that is very possible in that we have something in which on both sides it's larger on both sides, okay? And the thing is, we pretend, right, this is sectioned off, okay? Almost like as if you have a picture and you took a snapshot, okay? And there might be other things outside, right? It might be like this, right? We might have a crazy graph like this. But idea is I'm focused only on the situation at hand where I'm only looking inside this. I'm going to make this red box. Everyone see that? So even though obviously outside, right, there's a lot of other things happening, inside this box, this blue dot is the largest point on both sides. So it's a local max, okay? And then local min is essentially the same thing. It's going to be a section off boundary on both sides, but it's just going to be the smallest situation here. So something like this. Okay, for the following right here. So now one thing we want to understand is that endpoints will never be a local max or a local min. okay, because it has to apply on both sides. Okay, so something like this, right, is not a local max because it has to be coming from both sides. Okay, so if you notice there's nothing on the right that's smaller, so hence it's not a local max or local min. Okay. So that is the first type of minimums and maximums. What we're going to do next is we're going to go over extreme max and minimums. Okay, so I'm going to scroll down right here. And so we have what's called extreme or absolute max and mins. Okay, so what's the difference between absolute versus local? So local, remember, is under its confined space, and absolute means the largest or the smallest out of the entire graph. Okay, so for the following right here. Okay, absolute max and min must be a finite value. Okay, so that's something to be mindful of. Okay, so absolute means essentially largest or smallest for all, and then local means largest or smallest in that confined space. Okay. Okay. And then one last thing we want to talk about is what's called extreme value theorem. So if f is a continuous function, so that means if it's continuous, then it must have an absolute max and an absolute min, okay, for the following. So for example, like let's say I have a graph like this. Okay, and we cut off the boundaries. We can clearly see this is an absolute min and this is an absolute max, okay? Now, as you can see though, these are not local mins or local max, right? Because local min and max has to be on both sides, okay? Absolute min and absolute max has to be the largest or smallest out of the entire graph, okay? For the following here, okay? So we're going to do some examples. We're going to talk about how to find local mins and max, how to find absolute min and max, and also the intervals of when it's increasing and decreasing. Okay, and some of these can get kind of tricky depending on the situation you're in. Okay, and it's possible to have both. Sometimes it's possible to have none. Well, I'm going to kind of show you in a couple of these here. Okay, so let's look at this here. So I'm going to look at the following. So I have this graph right here, and I'm trying to figure out what my local minimums are. Okay, so remember, local minimum is minimum under this confined space that will be the smallest out of both sides. So for example, if I look at this here, right, this picture right here, okay, I'm confining my graph into this area. This one is smaller on both sides, so my local min has to be 0, 0. I'm writing it as a coordinate, okay? Because everyone see that? Because if you look at the left and the right, the graph is larger, okay? And also, let me clarify, when I'm saying larger, I'm talking about specifically the y value, right? So if I'm looking to the left and the right, they have larger y values, okay? Local max, I actually have two. I have one right here, and I have one right here. Okay, you don't have to sketch it as you're doing this. I'm just kind of showing you. I'm just pointing it out to you. But as you can see, right, they're both hills, and they're both kind of little hills. Okay, and that's also another That's also another reason for you guys to determine local max and mins. Okay, local maxes tend to look like hills. Okay, and local mins tend to look like valleys. Okay, so I have this one. So this is negative 216 and 216. Okay. I'll do increasing and decreasing later on. Let's look at part D and part E, okay? So part D says, what is your smallest number or your absolute min? So we're saying, what is the smallest y value out of the entire graph? So if I look at this graph here, this one is my smallest point, and it looks like it's approximately 3, negative 10. Okay? And then my absolute max actually is my largest y value, So I can say this is negative 216, or I can say 216 as well, okay, for the following, okay? When you're answering this question, they may ask you to write it in coordinate, or you can write it as a y value, so you can just say y is equal to 16. That is also appropriate as well, okay? But one thing you should notice here, which is kind of interesting, is if you notice, my local max is actually my absolute max, and that is possible, okay? It is possible to have your local and absolute be exactly the same. It's possible that neither of them would actually exist for the following. Okay, when you're doing these type of problems, there's a lot of different situations that can arise. Okay, so I'm going to do part C last. Okay, so I'm saying when is it increasing or decreasing? So let's talk about increasing and decreasing here. I'm just going to erase this as I'm talking. When we talk about increase and decrease, right? Obviously, that's when increasing when it's going up, decreasing when it's going down. Okay. One thing is, okay, here's a way to kind of, here's a analogy I'm going to use, right? Pretend it's almost like a roller coaster. Okay. Increasing is obviously when your roller coaster goes up, decreasing when it's obviously going down. If you're riding a roller coaster, right? There's always a part where, right, it's always going to just break or stop, right? Like before, right, your roller coaster goes down. At that point, your roller coaster in that position, right, before you go down, you're technically not increasing and decreasing, so we don't count that. Okay? So when you're at that highest point right before you fall, right, that's technically not increasing or decreasing. Same thing once you hit the very bottom before you bounce back up, that is neither increasing or decreasing. So we don't include those. Okay? So when I'm looking at something, whether something is increasing, okay, one thing is we want to write this in interval notation, okay? So it's increasing from the following, okay? And actually, interval notation will always be parentheses. So it's going to be increasing from, let's do approximately negative 2.5. Remember, I'm using my x values when it's increasing, not my y's. I'm starting around negative 2.5. It's going up to negative 2. I am not including 2 because it stops right there. Okay? And then I'm going to use union, right? Union, if you recall, means I'm including several intervals, right? So I'm going from negative 2.5 to negative 2. And it's also increasing from 0 to 2 right here, okay? I'm not including 2 because notice it stops at 2. Okay. So let's do decreasing. I'm just going to use a different color to kind of show you what's happening. So for decreasing, it's decreasing in these parts, right? So it's going to look like this. So decreasing is from negative 2 to 0. Notice, right, we don't include 0 because it's kind of it's at the part where it doesn't increase or decrease. And then union 0, and then, union from 2, and it looks like it stops at 3. That will be my final answer. Okay, so let's do one more example. I'm going to do the top one. I'm not sure why I did a bottom one first, but let's look at this top one here. And same thing. So I'm going to find my local min, right? So my local min, right, remember, is your valley. And that one is going to be 3 comma negative 1. And then local max is going to be negative 2 comma 6, right? Because it is, right, negative 2 comma 6 is the highest on both sides. Minimum is smallest on both sides. One thing too is we're going to be drawing arrows here. Sorry. Yeah, pretend they're arrows, okay? So if you notice here, because we have arrows, right, this graph is continuously going up, this graph is continuously going down. And they ask you, what is your absolute min? Okay, your absolute min, you actually don't have any because your graph continuously goes down, right? If you look up here, right, if you look back up to your notes, absolute max and min must be a finite value, right? There has to be a y value for the following, okay? So if you know, since it's continuously going down, we technically don't have an absolute min. And then therefore, since our graph is also going up, we technically don't have a largest y value, okay? A way to think about this too is like you can't, right, is because you can't technically reach it, right? So for example, like let's say you think absolute max is y is equal to 20. Because my graph continuously goes up, I can argue like, well, technically it's not 20 because there's something larger that's 21, and that's 22, right? And I just can keep going up and up and up, and I won't actually hit a finite value, okay? So that's why, because both of them actually hit negative infinity and infinity respectively, we don't have a absolute min or an absolute max. So in an interval of increasing and decreasing, so let's take a look at this here. So increasing, we're going from negative infinity to negative 2, union 3 to infinity. Okay? Notice it's increasing. Kind of look at how it's drawn. And it's increasing like the following here. And then decreasing will be this part. And it's going to be from negative 2, 3. Okay. So make sure you practice these. Some of these can get a little tricky, okay? And remember, because there's a lot of different types of varieties with these types of problems, you can have a lot of different case situations that could arise, okay? You could have many local mins and local max. You may have none. You could have many absolute mins and absolute max. You may have none. You could also have absolute mins be your locals, okay? There's a lot of different possibilities that can happen for the following, okay? So that is another part of 2.0.